Okay, so welcome to the final day of this conference. So our first speaker today is Subhash Khot. So Subhash did his PhD in Princeton and now he's a professor in NYU. So Subhash is also a fellow Nevelina, or I guess Abacus Prize winner, formerly known as Nevelina Award. And today is going to talk about CSPs. So take it away, Subhash.
Okay, yeah, thanks for the introduction. Thanks for the invitation. Nice to be here. Best wishes for Mark. And as it turns out, at least part of the work I will talk about is joint with Mark. So this is the title, Approximating CSPs or Constraint Satisfaction Problems on Satisfiable Instances. And this is brief, just outline of the talk. So that's the main central issue from the computer science side, approximability of CSPs. And it turns out to answer this question, one has to answer analytic questions, which is understanding expectations of this kind. So we'll get to this. And then it turned out that it has many applications to additive combinatorics, parallel repetitions theorems, property testing, of course, analysis itself, and potentially perhaps to getting analytic proof of what's known as the dichotomy theorem. And even more speculatively, perhaps to get lower bounds in communication complexity in the so-called number on forehead model. And this we started doing about 5 years ago. This is all joined with Amey Bhangale, Dor Minzer, much of it also with Yang Liu, and some with Mark and Kunal Mittal. And feel free to interrupt anytime. I hope, I mean, the talk is going to be very high level, but I do hope to give a sense of at least a little bit of everything. So I'll start with just mentioning the applications, let's say to additive combinatorics, which would be very at least straightforward to state. I hope everything is visible. So it is a well-studied question in additive combinatorics. Suppose I have a subset of fp to the n, which is free of 3 APs. So it's 3 AP free, meaning it does not contain arithmetic progression of size 3. So what's an arithmetic progression of size 3 is just a pair of triple of points x plus a, x plus 2a, and a is a non-zero vector, and these are all vectors in fp to the n. And the question is, how large can a set be and still be 3 AP free? Now, this question is also considered over integers, and perhaps I think it's even more well studied over integers. And there we do have excellent upper bounds, works of Roth, Zamaredi, Gowers, and more recently Kelly and Mecca. So here we will consider the question over fp to the n, which is also very well studied. And it's known that the density of any such set, meaning relative size compared to the whole space, is in fact exponentially small in n. And these are results of starting with Roth, then Meshulam, and Ellenberg and Giswith. So there is a related question which was raised by Ben Green and also Hasla. Yeah.
Is there any dependence on P?
Yeah, there could be some dependence here. Right? Yeah. P I'm thought of as like 5. In fact, Ben Green says 5 is my favorite prime. So this is a related question. This was raised by Ben Green as well as Hasla, Hollenstein, Mossel, that what if I want to be restricted 3 AP free, meaning I only want to be free of APs of specific kind where the common difference is a 0, 1 vector, right? Not some arbitrary fp to the n. Okay, and can you still prove upper bounds on sets which are free of these restricted 3 APs. And turned out this was open, and we were able to answer this and show that this is at most something like this. I mean, using all our work and framework and such things. Now, let me quickly tell you how such results are proved. At least maybe the first one. So, natural approach is Fourier analytic. So you say you let the function f to be the indicator of the set A, and try to show that if the set A is large enough, then not only that it actually contains a 3 AP, in fact, it contains a constant fraction of 3 APs when a 3 AP is chosen at random. Okay. So how do you choose a 3 AP at random? You simply pick x plus a, x plus 2a at random. X and a are random, right? Which amounts to picking on each coordinate xi as a random element of fp. Then you say the next coordinate is xi plus ai, and then it's xi plus 2ai, right? On each coordinate independently. And ai would also be a random element of fp. Right? So this is some distribution mu on fp to the 3, right? And you pick 3 points from product distribution mu to the n. Okay? This is how you would pick a random 3 AP. And you would like to analyze the following quantity. So expected value of f of x, f of y, f of z. F is the indicator of the set. So if I pick a random AP according to this distribution, this is exactly the fraction of the APs which fall into that set. Okay, and now you can naturally see how these expectations arise. Certainly from this additive combinatorics question, but they, from our perspective, they arose quite naturally from CSPs, studying CSPs. And in this case, just the 3 AP question, where the standard 3 AP question, it turns out this expression has a nice Fourier analytic form. So roughly speaking, it's something like this. Sum of cubes of Fourier coefficients. Okay, so let's not get into technicalities. And if the set is 3 AP free, then it immediately implies that the sum of the third powers of Fourier coefficients has to be large. Okay, which means that there must be one Fourier coefficient which is large, which amounts to saying that the Fourier coefficient defines a subspace of fp to the n. It simply means that if you zoom into that subspace, the density of the set increases. Okay, so you go into that subspace. Now you have a set of larger density, and you just repeat the argument. This is called the density argument, increment argument, and eventually you reach a contradiction when the set essentially consumes the whole space. So this is the proof in the standard 3 AP case, but in the restricted 3 AP case, when you now again you have the same distribution over APs mu to the n, except that in the base distribution on one coordinate, the common difference ai is only a 0, 1 coordinate. Okay. And then it turns out this basically just falls apart, the standard argument. But as I said, we can still prove this upper bound like this, which in this literature is referred to as a still reasonable upper bound. Okay, because in this literature there are upper bounds which are so weak. In fact, we will see that these are still called reasonable. Yes.
What's the truth?
Who knows? Yeah, yeah. Could be still exponentially small, right? All right. So that's the first application to additive combinatorics. Yeah.
If the restriction on A is some other two-element set to the end, is it possible that that change quantitatively changes the down?
Our methods would give the same, and it would still be open.
But there's no formal reason to expect the answer to be the same independent of the two-element sets.
Yeah, there is no reason.
When you restrict to this subspace, don't you lose the dependence of the
No, because it's x plus a, x plus 2a. It's sort of basis independent. All right. So the next application.
Any construction known better than the for this setting than for the
Yeah, I think this restricted 3AP. I don't think this was. I mean, this is like super well studied. It was posed more like a curiosity or like as a challenge to our current methods. So I don't think people invested too much effort into constructions. Any case, so the next application is to what's referred to as the density Hell's-Jewett theorem. So again, it's a similar problem. You have a subset of 0, 1, 2 to the n, and you want to be free of what's referred to as a combinatorial line. So combinatorial line free. And what's a combinatorial line? It's again a set of 3 points x, y, z in the space 0, 1, 2 to the n, such that on each coordinate xi, yi, zi is either equal 0, 0, 0, 1, 1, 1, 2, 2, 2, or 0, 1, 2 in that specific order. Okay, this is what a combinatorial line is. And again, the same question: how large can this set be without containing the combinatorial line? So the Hells and Jewett, they in I think roughly 70, they proved a coloring version of this problem, meaning if I color for sufficiently large n, if I color this space with some constant number of colors, then there is at least one color class which does contain a combinatorial line. Okay. On the other hand, to proving the density version, meaning just showing that any set of large enough density has a combinatorial line, this was surprisingly difficult, and this was only done in early 90s by Furstenberg and Katz-Nelson using ergodic methods. And they did show that at least as n tends to infinity, the density does tend to 0. But because of the methods, they did not give any constructive or explicit bounds as a function of n. And this was achieved only in the polymath project in roughly 2010. So this was the polymath project number 1. This was initiated by Gowers, Tao, also from computer science side, Ryan O'Donnell, and there was a large team of online open collaboration. And they did show that this is at most something like 1 over log star n, maybe 1 over square root log star n if one wants to be precise, yeah, which is weak bound. And now we are able to show the reasonable bound, something like, maybe we need 4 logs here, but it doesn't really matter so much. We can show this. And the nice thing about this Hell's-Jewett result, or these combinatorial lines, that you can already see that this is already an AP. Okay, in fact, it's an AP of even restricted kind. So this primitive is perhaps the most basic one, that it already qualifies as a special case of many other things. So if once you have upper bounds for this, you automatically get upper bounds for pretty much everything. Okay. For example, you would get automatic upper bounds to the parallel repetition theorems, for example, or right, APs, of course. All right, so we can do this. So the next application to parallel repetition. I will describe a game called G at Z game. It's a game between 3 players A, B, C, and there is a verifier V. The verifier sends questions to the players, called the questions X, Y, Z. These are bits, such that X plus Y plus Z is 0 mod 2. And the players are supposed to give back answers. Let's call the answers A, B, and C. These are also bits. And the verifier accepts if mod 2, A plus B plus C is X or Y or Z. I mean, that's the game. This was studied in the quantum information studies. And so what's the value of the game? The value of the game is defined to be the maximum probability with which the provers can make the verifier accept. And the provers can use whatever strategy they want, but without talking to each other. Right? Now, if this acceptance predicate was simply A plus B plus C equals X plus Y plus Z, then the provers could return the same answer and simply they would make it accept with probability 1. But because of this non-linearity, you don't hope that there would be a success probability 1 strategy. On the other hand, since there are only 4 possible question triples, right? You can easily devise a strategy where the provers get it correct 3 out of 4 times. And indeed, the value of the game is in fact 3/4. And the parallel repetition question is, what if this game is repeated in parallel, meaning now, let's say to the first prover, for some parameter n, the question is n tuple of questions independently. Okay? And the answers are also now A1 up to AN, presumably giving answer for each coordinate. And similarly for all 3 players, and the verifier accepts if he would have accepted on each coordinate. Okay. Now the question is now the same: what's the maximum probability with which the provers can convince the verifier? Okay. Now you would hope that if the provers simply use the same strategy on every coordinate independently, then it would certainly be 3/4 to the n. But turns out that the provers could have more sophisticated cheating ways of answering, where the answers on different coordinates could somehow be correlated. And you would still like to prove upper bounds on the value of g to the n. And this turns out to be actually surprisingly difficult task. For 2 prover games, Ran Raz in mid-90s, he did show exponential lower bound. So this is for the 2-player games. You can these are 3 players. You could have the same kind of games for 2-player games. On the other hand, for the 3-player games, it's still open to prove a bound which decays exponentially with n. And in fact, this particular game called the G at Z game, this was viewed as a hurdle towards making progress. And Holmerin, Raz, Girish, Mittal, and Jan, they did show a bound which goes down polynomially in n. And in a result with Mark and Dor, we did show for the GHZ game that the bound does go, it does decay exponentially, and somehow we sort of hit upon this proof, half of it by accident, half of it by actually what we were considering from the CSP viewpoint, what I would, towards the end of the talk, would refer to as abelian embeddings. Okay, so what we sort of observed is that even though this predicate looks nonlinear, it is nonlinear over mod 2. But somehow, if you think of the same predicate over modulo 4, it's actually linear. It's actually quite cute, surprising fact. And then we can use our methods. Now, as I said, this is still open for general 3-player games to proving exponentially decay bounds. I mean, there are things known. So there is a result of Dinur, Harsha, Venkat, and UN, which shows exponential decay for games which are called connected games. I will maybe later on I will say what connectedness amounts to, and we were able to also show these for family of games called 3 XOR games, projection games, maybe a bit more, but overall this still remains an open problem. Yes. GHZ with K players. Meaning you would have try having the same predicate. Yeah, I don't really know. So first thing we would check is whether it also becomes linear or mod 4, maybe some mod 8, who knows? Yeah, I can't think of any quick reason why it does become mod 4. Every time I have to just check it by myself. Yeah.
If the provers can share entangled qubits,
so that's exactly. So that's the quantum connection. That in the quantum world, actually, the provers do have a perfect strategy if they share entanglement. So it's a game where the quantum value is 1, but the classical value is 3/4. Yeah. All right. So let's move on to the next application to property testing. So suppose you have a function f, which is a function from f2 to the n to f2, and you want to check if the function is linear over f2. So you could devise the following test. You pick 3 random inputs x, y, z, and check if f of x plus y plus z equals fx plus fy plus fz. Everything over f2. And you hope that if this test passes with probability high enough, then the function is close to being linear, right? And these are the kind of results which are sought after in the area of property testing. And in fact, this turns out to be correct. So this is probability over random choice of x, y, z. So if f is linear, then certainly this probability is 1, right? So you expect that if the probability is close to 1, then the function is close to being linear in Hamming distance, except for some maybe order epsilon of the inputs. And that indeed is true. So if this passes with probability 1 minus epsilon, then f is in fact close to, in fact, epsilon close to linear. And this is famously known as the Blum-Luby-Rubinfeld test and the analysis. It's very important in probabilistically checkable proofs and some related areas. Now you could ask a more challenging question. What if this probability just little bit exceeds 1/2? right? And can you still say something meaningful about the function? And again, turns out the answer is yes. You can show that. I mean, you cannot expect now f to be completely close to a linear function, but still you can show that f is correlated with a linear function. Correlated, formally it would mean expected value of f of x times, let's say L is some linear function, L of x, where instead of now, when you compute this expectation, these functions are viewed as +1 - 1 instead of 0, 1. And then that's the correlation. Okay. So you can say that the function is correlated with a linear function, which is just another way of saying that the function has a high Fourier coefficient. And this was proved by Bellare, Coppersmith, Hastad, Kiwi, and Sudan. This is well known. And now the question which was open was, what if all my inputs are over mu p bias distribution, meaning it's a distribution of 0, 1 to the n, where each bit is 1 with probability p and 0 with probability 1 minus p. So now you have a bias distribution on the cube. And you would still want to ask the same question. If now my x, y, z are inputs from mu p to the n, and what if this holds with probability 1 minus epsilon or half plus epsilon? Okay. Though here you need to be a bit more careful, because if you just picked x, y, z completely independently, then actually x plus y plus z would not be distributed according to mu p. So you need to be a little more careful so that all 4 inputs are by themselves distributed according to mu p. That can be done. And the same question, if this is at least 1 minus epsilon, then actually it is true that the function is still close to being linear under the same product distribution mu p to the n. And this was showed by Dinur, Filmus, and Harsha. And what was open was, again, the half plus epsilon case. So what can you say about this? And we can answer this case, essentially showing that it is still true that the function is correlated with a linear function. Though here the answer gets more complicated. There is some relationship between, so formally this is true only for p which is between 1/3 and 1/2. Below 1/3, in fact, we can show that actually this conclusion is not even correct. What is correct then is that the function is correlated with a linear function times a low degree function. Okay. But any case, so that's the application to property testing. And now we will get back to actually the, at least as far as we are concerned, the main motivation. This is approximating CSPs on satisfiable instances. Yeah.
I feel like you should know this, but is there a reason why you have to take 3 inputs rather than 2 inputs?
Yeah, that's also fine. In the standard setting, in fact, this is in fact done with only x plus y equals fx plus fy. In this case, I think yeah, one can show that it just doesn't work with 3 inputs. All right, now the CSPs. I can continue here. So approximating CSPs on satisfiable instances. So there are 2 important ones, the satisfiable, and maybe I should have said approximating all CSPs on satisfiable instances. So that's the question. So let me explain the question. So what are CSPs, or constraint satisfaction problems? This is a very natural family of computational problems. In particular, 3-SAT is a CSP. So what's 3-SAT? You have variables x1 to xn, and you have constraints where a typical constraint looks like this, maybe x1 or x2 or x3. You could have negations, maybe x sub n or x sub 7 or x sub 5. Maybe you could have negations. And these variables are supposed to be 0, 1 value or false and true value. Okay. And the instance is called satisfiable if there is a value you can assign to the variables which satisfies all the constraints. Okay. And this is a well-known NP-complete problem. Given an instance which has a satisfying assignment, can you actually find the satisfying assignments? That's NP-complete. So the next thing you could hope for is to seek approximation, meaning I promise you that the instance is satisfiable. Find me an assignment that satisfies as many constraints as possible. Okay, so that's the goal. Given a satisfiable instance, find an assignment, find assignment satisfying maximum fraction of constraints. Now, what's possible to do for 3-SAT is certainly you can simply take random true-false assignments to the variables. Right? And if you take a random assignment, how many constraints do you hope to satisfy? 7 over 8 fraction, right? So you can certainly do 7 over 8 fraction. And a very well-known like spectacular result of Johann Hastad is that in fact it's NP hard to do better than that. So you can certainly do 7/8, but finding 7/8 plus epsilon satisfying assignments is itself an NP-complete problem. So for 3-SAT, we know the exact threshold 7/8. Okay, and our overall project is to understand or figure out these precise thresholds for every constraint satisfaction problem, because a CSP is defined by a template constraint, which for the 3-SAT is OR of 3 variables. But I'll give you more examples of CSPs, and you will see that these answers or thresholds they're going to be different. So in particular, for example, so let's even note down here what the algorithm which works. So this is random assignment.
That works for any, even a non-satisfiable one, right?
Yes, yes.
Is the hardness also known even for things which are satisfiable?
Yes, yes. So for 3-SAT, it's also known on satisfiable instances. Okay. Now for 3-lin, which is some CSP is similar, except that the constraints are linear, meaning x plus y plus z is 0 mod 2. Okay, mod 2. These are just linear equations. Okay. Now, if I tell you that there is an assignment which satisfies all constraints, how well can you do? You can find it, because you use Gaussian elimination. You can find the assignment which satisfies all constraints. So in fact, this is you can call the threshold to be 1 in this case, or you could simply say that the problem is in P. It's polynomial time solvable. Okay. And what works here is just Gaussian elimination. Let's make it more interesting. Let's make it 3-lin, but over some presumably non-abelian group G. Meaning here the constraints would be of the type xyz equals maybe some constant over some perhaps non-abelian group G. Okay. And turns out here also we know the exact answer. The answer is 1 divided by the size of the so-called commutator subgroup of the group. Then that's it. So if the group is abelian, the commutator subgroup is just trivial. So you get 1. Okay. Otherwise, you get some non-trivial threshold, and it can be shown that this is optimal. And the algorithm is, at least in hindsight, it's clear what you want to do. So you have equations of this type. You can reduce these equations by moving on to the quotient space, by quotient of the group, by the commutator subgroup. So these x twiddle, y twiddle, z twiddle, maybe b twiddle, these would be the coset representatives, right? Now at that level, once you have quotiented out by the commutator subgroup, your group is abelian. And therefore, you can solve it. You can find a perfectly satisfying assignment to this reduced system. And then from each coset, you can go back and pick one element at random, right? And therefore, that's why you would get this. All right. And here, I mean, it's a combination of random assignment plus Gaussian elimination, which is a bit clever. This is true. Let's move on. Let's look at graph coloring, where you have a graph G, and you have colors. Let's call them 0, 1, 2, 3 colors, and the predicate is simply x0 equals y. That's graph coloring. So here the problem is simply, I give a graph, I tell you that is 3 colorable. Find me a coloring which properly colors as many edges as possible. How best you can do. I don't think we know actually answer for this, but there is a strong evidence that there is some threshold S, which I think I can even tell you. I'm not sure, but I mean, you can take it to the bank. I think that's the expression. That there is a threshold S, which is likely to be the tie threshold, and one can also show that from the algorithmic side, the best algorithm which achieves that threshold is semi-definite programming relaxation and rounding. Yeah, right. No. You can only use 2 colors, 3 colors. Yeah, right. Yeah. So the algorithm would be STP relaxation plus rounding. And so this just gives you a flavor of what we are looking for. Given any CSP, what's the optimal algorithm? And you have to show that the algorithm is optimal by also showing a matching hardness result. Okay. Now here is a problem which is quite interesting, and we were able to make progress. So this is called the rainbow hypergraph coloring. Yeah.
For graph coloring, is a constant, or that thing depends on it?
For graph coloring, there is some constant S, meaning modulo some conjectures, this and that.
Depending on the number of colors, right?
Yes. But here I said you have 3 colors. Yes.
So then wouldn't that give you an algorithm for approximate coloring? You repeat it k times and then you take it.
No.
Create a vector
No, because you will have to do log n times.
Yes, depending on.
No. This does. I can assure you, this does not give algorithm to actually color the graph. Okay. Yeah.
So that is you're not telling us what this constant is, but there exists an exact constant that you know.
I wouldn't say there exists. I strongly believe I can give a convincing argument. There is no formal proof. Okay. Yeah, maybe I should have said this beforehand, that this whole question in its full generality, it's just so challenging that I'm perfectly okay making all kinds of conjectures, just to gain understanding. Okay. So the interesting one where one could say something interesting is a rainbow hypergraph coloring, which is you have a 3 uniform hypergraph, 3 colors, 0, 1, 2, and the predicate is now the hyperedge is it's a triple XYZ, and you get a credit if you do use all 3 colors to color that. So meaning the 3 colors are distinct. Right. And now for maybe the next 5-7 minutes, let's focus on what we can do on this problem. So this is the rainbow coloring. So we have this hypergraph, these hyper edges. Let's call a typical hyper edge X, Y, Z. And you are given that it is rainbow 3 colorable, and you are trying to find as good coloring as possible. Now, suppose you are in the shoes of an algorithm designer. Now, since you want as good algorithm as possible, I mean, you got to throw every algorithmic tool that you can think of. Okay. Now, certainly you can all CSPs. They have a natural algorithm based on semi-definite programming relaxation. So I'm not going to define it; it's a bit cumbersome. But there is one. And what the SDP relaxation would do is, to every variable x, variable or vertex, it comes up with a unit vector. Let's call it v sub x. So, for example, if you know the max cut algorithm, Gomans-Williamson, for every variable you get a unit vector, and this is a vector which is a unit vector in Rn, where n is, let's say, the number of vertices in the instance. And then there is a rounding method, which is project these vectors on let's say a line, and then depending on how the projection looks like, color the vertex by one of the 3 colors, 0, 1, or 2. Okay? So that would be the standard SDP rounding. So I can abstract it out by saying fix some rounding function, call it psi. It's a function from reals to the 3 colors 0, 1, 2. And what I intend to do is project all these unit vector v sub x's onto a line, and then color according to that. So formally, I could pick a standard Gaussian G in Rn, and then color x with the following color. The projection of the vector Vx onto a random line is really just the inner product of Vx with G. And then apply your rounding function psi to that. And that's it. This is my coloring. In fact, if you know, this is exactly how Gomans-Williamson works. You take this and then just look at its sign, plus or minus. In general, you can do it for any CSP. Yes, maybe I should have said this before, is there was a question asked, what happens on instances which are near satisfiable as opposed to perfectly satisfiable? So there the picture is completely different. For example, for 3-lin, on perfectly satisfiable instances, you can find the satisfying assignment, whereas if it's only nearly satisfiable, actually you cannot beat even 1/2. That's another well-known result. Okay. And you can ask the same question, can you find best algorithm for every CSP on near satisfiable instances? The near satisfiable instances is actually fully answered. And this is the work of Prasad Raghavendra. In fact, he shows that an SDP relaxation and rounding, pretty much exactly like this, is an optimal algorithm on near satisfiable instances. Okay. But for us, it's really important that we are working on fully satisfiable instances. Now, in this case, there is something else you could actually do, given the promise that the instance is fully satisfiable, which a priori is not clear. But once I tell you, you will immediately say, yes, it could be done. So what you observe is that it's rainbow 3 colorable. So if these are the colors x, y, z, they are 0, 1, 2 in some order, and therefore I always know that their sum is 0 over F3. Okay. So in fact, you can think of it as a system of linear equations over F3, and that system you could solve, right? And hope that somehow it helps. Okay. And since you're an algorithm designer, you got to use every tool that you have. Okay. Yeah, so solve this F3 linear system. And you could use the solution space somehow. And I'm going to propose a similar rounding in this case. In fact, what I will do is I will simply sample from the solution space uniformly at random, solution space of this F3 linear system. And then that in particular for every x is going to give me a value called bx, which is at 0, 1, 2. Okay. And maybe that's my coloring. Okay, why not? Okay. Now, just to be sure, it's not going to color all the edges properly because there are going to be edges which will end up getting 0, 0, 0 because the equation is satisfied, but it's not properly colored. Okay. And what we can show, I guess, after a fair amount of work, is that for this rainbow coloring problem, the optimal algorithm is likely to be a hybrid of these two. Hybrid algorithm and a hybrid rounding, where you would get a sample, one-dimensional projection. You also get a sample of this, and then you could color based on the two. Okay, so you could a priori fix a rounding function. Let's call it phi now. So this would be a function from R cross F3 to the colors 0, 1, 2. And you would color x with phi applied to both the projection, Vx inner product with G, and this value Bx. We can essentially show that this is very likely to be optimal, meaning we can match it with what is called analysis of a dictatorship test. Let's not get into that, but evidence which is, in this business is considered compelling. Yeah, so that no, so it's not going to actually pinpoint what that constant is. It will be in a more abstract sense. What it will say is the following: that depending on what phi you choose, in fact, you need to be more general. You could take k samples of each and then apply phi to collection of samples. So you could do that. So it's really a family of algorithms. And what we can show is that take the best algorithm in this family and let S be whatever, S star be the performance of the best algorithm from this family. And whatever that is, which is some non-explicit constant, that we can match from the hardness or dictatorship testing side. Yeah. This is the level of abstractness also the Prasad Raghavendra's result works. Yeah.
Do the Gaussian G and the F3 solution need to be sampled independently, or could you maybe gain something by correlating them?
Yeah, we sample them independently. And then actually prove a matching hardness result, which then somehow in hindsight justifies that, it's enough. Yeah.
Can one prove that either of them individually doesn't require whether it's combined?
Yeah, I guess in principle, which then would amount to at least getting some handle on all these numbers, which we really didn't bother. Yeah. No, not really. The Grothendieck is a different problem. It's not really a CSP because it's like a, it's a CSP with negative weighted constraints somehow. Though at the end of the day, there is some similarity, meaning even there, there is an SDP, there is a rounding, and to figure out what the best rounding scheme is, it amounts to solving some geometric isoperimetric type problems, which is also the case.
Not the like the actual actual identity that tells you
Ah,
there's the signs of the.
yeah, I mean, I don't see any more direct connection than what's evident. Yes.
Do you have any visibility into so in the 2CSP case, there is a connection also between SDP value and parallel repetition value of decay. Do you have any visibility into, do you expect this to hold here, or is
You mean for 3-player?
Yes. I mean, it's obviously we are barely able to prove anything, but while we are willing to make conjectures, do you believe that that's the right value, or if there is some third constant?
Yeah, it's not something I ever even thought about.
Or
and you're also the expert, so you didn't think about it either. So we should sit together. I think I've run out of time. In which case, I'm perfectly, happy to stop.